So in this video, we're going to establish the concepts driving the first derivative test, and then in subsequent videos, we'll show examples of how to apply the first derivative test. But here's the big idea. So in pre-calculus, you learned about calculus. You learned about local maxima and minima, or relative maxima or minima, and these were used as synonyms. And this summary slide right here comes right from a pre-calculus lecture PowerPoint. But all a local maxima or minima was in pre-calculus was you established an open interval from A to B. And then you looked on that open interval, and if you could find a spot on that open interval that was either the highest point that existed on that open interval or the lowest point that existed on that open interval, then you had a local minimum or a relative minimum. So those are synonyms. They mean the same thing. And similarly, if you were able to go anywhere for your function f of x and establish an open interval, let's say right here, and find that there was a highest point on that open interval, then that was a relative maximum on that interval, or local maximum. Again, those two phrases mean the same thing, local maximum. So for the picture that I see here, I could actually identify that I have two local minimums, two places for which I could establish open intervals, and those locations would be the lowest possible location on those open intervals. Oh, three. Here's one here too. I can establish an open interval here, and here's another local minimum. So I have three different locations where I have local minimums, or low points on my graph of f of x locally, and I have two locations. One's here, there's a maximum, and one's right here, there's a local maximum. And so in pre-calculus, what you did to identify the locations of the minimums and the maximums over open intervals is you just looked at the graph and you used the picture to identify where those maximums or minimums were. And the idea now is we want to be able to use calculus to identify the location of the maximum and minimums locally. And if we can use calculus to do it, that means we can find the locations of the local maxima and the local minima without having to look at the graph of the function. So here's the big idea regarding how to use calculus to locate local minimum or local maximum. So here's a graph showing the location of a relative or local minimum. And the key idea is that if you construct a tangent line on either side of that local minimum, you'll see on the left-hand side of the local minimum that the slope of that line is negative. In other words, the derivative is less than zero. The derivative, because the derivative describes the slopes of the tangent lines, the derivative is negative. So you're going from a situation where you have negative tangent line slopes to, at the relative minimum here, a slope of zero, and then transitioning to have positive slope. So here the derivative is greater than zero, or I have positive tangent line slopes. So to identify whether a critical number C, so you find the critical numbers, which are either going to occur when the derivative is zero or you have a sharp cusp. You find your critical number, and then you look at the slopes of the tangent lines to the left and the right of your critical number. And you say, do the tangent line slopes change from negative to positive? If they do, I know that at my critical number I have a minimum, or a local or relative minimum. However, if I'm at a maximum, if I calculate the critical number C, and then I look at the slope of the tangent lines, I see that the tangent line slope will change from positive to negative slope as I step over the critical number. So if I change from positive to negative for my derivative, because the derivative describes the slopes of the tangent lines. If my derivative changes from positive, in other words, it's greater than 0, derivative or slope of the tangent line changes from positive to negative. As you step over the critical number, you know the critical number is at a relative maximum. Just because you find a critical number doesn't mean that you have a max or min. So here's two spots where the derivative is equal to 0. So at C, we see f prime of C is equal to 0. Here, f prime of C is going to equal 0. So we have critical numbers. So if the tangent line slopes don't change, so here the tangent lines to the left of the critical number are positive, and to the right of the critical number, the slope of the tangent line is still positive. So if you don't get a sign change, you don't have a max or min. Again, here the derivative or slope of the tangent line is negative. Here's the critical number where the derivative went to 0, but the derivative is still negative when I step over the critical number. So I don't have a max or min. I just had a momentary spot where the derivative was 0 and then it went negative again. So the key idea is using the first derivative test to find locations of local minima and local maxima. Find those critical numbers first. Find the critical numbers. And then look at the derivative and ask yourself, does the derivative change from negative to positive at the critical number? If it changes from negative to positive, the critical number was at a minimum. Look at the critical number. Look at the derivative as you step over the critical number. Does it change from positive to negative as you step across that critical number? If as you step across the critical number x equal to c, you change from positive to negative for the slopes of the tangent lines, you know you're at a maximum. If there's no sign change at all, so you're either negative on both sides or you're positive on both sides of your critical number, then you don't have a minimum, nor do you have a maximum at that spot. So that's the first derivative test. All the first derivative test is use the derivative as you look at a possible location of a min or max. Use the change in sign of the derivative to determine whether you have a relative minimum or maximum, which allows you to find the relative min or max without having to look at the graph of the function.